Dear all students, welcome to the VLSI testing class. Today we are going to talk about memory testing. First of all, let's introduce useful RAM4 models. For a single cell, a stuck at 4 SAF means that a cell is always stuck at logic value 0 SA0 or logic value 1 SA1. A transition fault TF means that a cell fails to make a rising transition from 0 to 1, or it fails to make a falling transition from 1 to 0. The notation used in this lecture is like this. S/F indicate a fault in a cell, where S is a value or operation that activates the fault. The notation S can be either 0, which means the cell is 0, or 1, which means the cell is 1. An upward arrow indicates that cell is making a rising transition from 0 to 1. A downward arrow means a falling transition from 1 to 0. An up-down arrow indicates either a rising or a falling transition. Letter upside down A indicate any operation. The value F means the value of the faulty cell, where F can be either 0 or 1 or up-down arrow, which means the complement. Using this notation, we can see that the transition fault can be divided into two types. When the cell is making a rising transition, it is stuck at value 0. This is the first type. The other type occurs when the cell is making a falling transition, but it is stuck at 1. So we call this a transition fault. A coupling fault involves two cells. One is the victim cell, the other one is the aggressor cell. There are three types of coupling faults: state coupling fault CFSD, inversion coupling fault CFIN, and idempotent coupling fault CFID. Those faults are modeled based on the actual behavior of RAM cells. For the first type, state coupling fault occurs when a victim cell is forced to 0 or 1 if the aggressor cell is in the given state. There are four types of state coupling fault. When the aggressor is in the state 0, it can force the victim cell to be 1. So this is our notation here. In this lecture, S1 indicates the value or operation that activates the fault in the aggressor, where S2 is the value or operation that activates the fault in victim. F is the faulty value of the victim cell. For the second type of state coupling fault, where the aggressor is in the state 0, it forces the victim cell to be value 0. Similarly, we have the other two types of state coupling fault. The second type of coupling fault is inversion coupling fault CFIN. It means that the victim cell is complemented if the aggressor cell rises or falls. There are two types of inversion coupling fault. The first one occurs when we have a rising transition in the aggressor cell the content of the victim cell will be complemented, no matter which state the victim cell was originally in. The other one is similar, except that the aggressor is now making a folding transition. The third type of state coupling fault, idempotent coupling fault, occurs when the victim cell is forced to 0 or 1 if the aggressor cell rises or falls. There are 4 types. The first type occurs when A rises. The value of victim is stuck at 1. The second type occurs when A rises, the victim cell is forced to 0. The other 2 types are similar, except that the aggressor cell is making a folding transition. The address decoder fault, AF, can be divided into 4 types. Type number 1. Given a certain address, no cell will be accessed. Type number 2. A certain cell is never accessed by any address. Type number 3. A certain cell can be accessed by multiple addresses. Type number 4. Given a certain address, multiple cells are accessed at the same time. For example, in the following figure, address A1 and A2 are 2 different cells. The value of A1 is 0 and the value of A2 is 1. If we read A1, we access A2 at the same time. So, what would be the output? There are 2 types of fault. The N-type address decoder fault would output a 0. On the contrary, the OR type of address decoder fault would output a 1. The type 1, 2, 3 address decoder fault are easy to detect, so in this lecture, we focus on type 4 only. Now, let's see how we can test the memories. We will introduce the famous March algorithm, which is the most widely known algorithm for testing memories. March algorithm is a class of many different algorithms, such as Math, Math Plus, and so on. They all belong to the March algorithm. The March test algorithm contains a finite sequence of March elements. A March element has 3 components. The first component is the memory operation. It can be either a read or a write. The letter R represents the read operation. R0 means that we are reading an expected 0. R1 means that we are reading an expected 1. The letter W represents the write operation. W0 means that we are writing a 0 to a cell. W1 means that we are writing a 1 to a cell. The second component to the March element is the data pattern, which is also known as the data background or background pattern. A data pattern means the data value we are reading or writing from a cell. The third component of the March algorithm is the address sequence. An upward arrow indicates the addresses are changing in ascending order. A downward arrow indicates that the addresses are changing in descending order. A up-down arrow indicates the address can be either ascending or descending order. The first March algorithm we will introduce is called MemTest. modified algorithm test sequence. It was first introduced in 1979. It is the shortest match algorithm that detects all the stochastic faults. MemTest algorithm has 3 match elements. In the first element, we are writing all cells to 0. It can be either ascending or descending address order. The second match algorithm read 0 and then write 1 in ascending address order. The third match algorithm read 1 in descending address order. Because we read both 0 and 1 from all the memory cells, so we detect all the stochastic faults. The complexity or the test time of MemTest algorithm is 4n, where n represents the number of cells. This is obvious because we perform 4 operations to each cell. So MemTest algorithm is the shortest match algorithm we can have. The MemTest algorithm also detects the address decoder fault. Consider the OR-type address decoder fault. Suppose that address A1 and A2 are accessed at the same time. Initially, we write all 0 to all the cells, and then we read 0 from a cell and write a 1. Suppose that cell A2 has been written to 1. When we are trying to access A1, at this time, the output of the operation would be a 1, since we are now considering an OR-type address decoder fault. So we can detect this fault using MemTest. On the other hand, if we want to consider the N-type address decoder fault, then we would need to have this MemTest algorithm. The operations are the same, but the values are now complemented. Both two types of MemTest algorithm detect only a half transition fault. In the first type MemTest algorithm, we only have 0 to 1 transition. In the second type of MemTest algorithm, we only have 1 to 0 transition. So we can detect only a half transition fault. This table is a summary of the MemTest algorithm. It detects all the stochastic fault, only a half address decoder fault, and a half transition fault, and the complexity is 4n. So now, can we improve the MemTest algorithm? If we want to detect both the N-type and OR-type MemTest, we can combine them into one match algorithm. We call this a MemTest plus algorithm. It detects both the OR-type address decoder fault, N-type address decoder fault, and of course all the stochastic fault. But still, we only detect a half transition fault, since we only have a 0 to 1 transition, but we don't have 1 to 0 transition. So the complexity is 5n, and we are missing half of the transition fault. If we want to detect all the transition fault, we can add one more read operation at the very end of the original MemTest plus algorithm. So we propose the MemTest plus algorithm. which is slightly longer than the math plus algorithm. The complexity is now 6n, but we are able to detect address decoder fault, stopgap fault, and all the transition fault. Now, we are only missing coupling fault. How can we detect all the coupling faults? Next, we will introduce the March X algorithm. It is interesting that March X algorithm has been used, but it has never been published in the paper. When we compare the March X algorithm with the previous Math++ algorithm, we see only a difference at the end. However, this small difference can make a big difference. The March X algorithm can detect the inversion coupling fault. Consider this inversion coupling fault when the aggressor is having a rising transition and the victim is complemented. In this figure, every row indicates a memory, and the victim cell is up here, the aggressor cell is down here. Initially, all the memory cells have been written to 0. Starting from the bottom, we read a 0 from the cell and immediately we write a 1 to that cell. When the aggressor is having a rising transition, the victim cell will be complemented. So at this time, the fault is activated. When we read a 0 and write a 1 to this cell, nothing happens. And then when we read from the victim cell, the good value should be 0, but the faulty value would be 1. At this time, we will detect this coupling fault. Now we will show that March algorithm can detect all the 4 possible cases of inversion coupling fault. The first case, where the aggressor is having a rising transition and the victim cell is complemented. This case has been shown in the previous slide. In the second case, we consider the same fault, where the aggressor is having a rising transition. But now the aggressor is on top of victim. We will write all the cell to 1. At this time, the victim cell will be complemented. So the fault has been activated. We use green color to indicate fault activation. Then, in the third March element, when we try to read a 1 from all the cells, at this time, we will detect the fault in the victim cell. Blue color indicates fault detection. In the third case, where the aggressor is having a falling transition and the victim cell is complemented, when we write a 0 to the aggressor cell, the fault will be activated. And then, when we read a 1 from the victim cell at the bottom, we can detect the fault. Now let's consider the fourth case, where the aggressor is still having a falling transition and the victim will be complemented. The only difference is now that a victim cell is at the top and the aggressor cell is at the bottom. Consider the last 2 March algorithm. When we write a 0 to the aggressor cell at the bottom at this time, the victim cell will be complemented. However, the fault is not yet detected. In the last March algorithm, when we read a 0 from all the cells, at this time we can detect the fault. So we have shown that The March X algorithm can detect all the 4 cases of inversion coupling fault. The complexity is the same, 6n, but it is better than the MemTest algorithm. Now it's your exercise to show that MemTest algorithm cannot detect all the inversion coupling fault, although the difference is very small. Now, there are some other coupling faults which are not detected by March X. So, the March C algorithm was proposed. The March C algorithm actually combines 2 March X algorithms together in opposite address order. The first half of the March C algorithm actually is the original March algorithm, and the second half of March C algorithm is actually the same as the March X algorithm with the address order changed. The March C algorithm can detect all the address decoder fault, stopgap fault, transition fault, and all the coupling fault, including the idempotent coupling fault and the state coupling fault. It's now your homework to show that March C algorithm detects these 2 types of coupling fault. The complexity of March C algorithm is 11n. However, there is one redundancy in the March C algorithm. Can you see which one? Yes, you can see that in the middle of the March C algorithm, we actually have 2 identical read 0 operations. We can actually remove this redundant read 0 operation, and we have this March C minus algorithm. The complexity of March C minus algorithm is 10n, and it detects all the faults. This is the shortest March test that can detect all the 4 faults. In summary, we have introduced different types of March algorithm, starting from the simplest math algorithm, which is 4n, all the way to the March C algorithm, whose complexity is 10n, and it detects all 4 types of faults. So March C is the shortest March algorithm that we can have to detect all the 4 types of faults. Thank you for listening.